Okay, hello everybody. I can see a few of you out there, so welcome back. I'm glad to have some of you with me for the live stream. So I'll go from the bottom. As an anecdote, that one kid, Sophia, Roxy, Lizzie, Farming Girl, Erica, Commander, Anna Banana, Alien, Academy, 420, and 0AX2. That's going to be awesome today, by the way, because we're doing Hex. Thanks for being here, and I know there's some other people out there, and I can't see your name, so sorry about that. If you're watching the video later, then I hope you've been having a good week. Um, okay, so, um, oh, D. Hawkins, hello. Magenta, hello. Um, hello, Zanana. So, good to see you guys out there. So all the grades are out, and everything looked good. In a couple of places, I just I don't think that was an issue really in this class, but when you put your name inside of your source code, please put first and last name, and just get in the habit of um, your work being formal in that way. And discussions on Piazza it can be less formal, but when you're submitting your programming work, I think it's just a good habit to be in that you treat it as something that's formal and wants a full name, that kind of stuff. Hello, Adeline or Adolin or Adolin. Hopefully, I got one of those is close to what it should be. Welcome. Okay, so second week, and we get to have a little bit more fun this week. I'll sort of just give you a heads up. It's going to feel. What is that? Oh, okay. Let me get that off the picture. But I want it. There we go. It was my mic. Okay, so it's going to feel this week we're doing two separate things. So we're going to spend some time talking about the way data is represented on the processor. That's hilarious in chat, Adeline. It's an awesome, good one. All right, so we're gonna talk about number systems, and then we're gonna do some continuing to kind of get up to speed quickly on using the HLA language. And we're just getting familiar with the high level parts of the HLA language, and pretty quickly you'll see that we'll start doing assembly type stuff in our programming work. But for the first couple of weeks at least, we just make sure that we have our environment working, that we know the basics of the HLA language, which is going to be very familiar to you because you've all had at least one semester of programming. And HLA looks like what most other C like languages look like. But anyway, numbering systems, HLA programming, and they're going to feel separate, but pretty quickly we're going to bring those together in our programming work. So just be patient about that, even though it's going to feel like this is kind of two different classes today. Number systems, HLA programming, but they come together pretty quickly. Anyway, so just heads up about that. We are. So Drew had asked, we're going to go over how memory storage registers buses work to reinforce the reading. And I will talk briefly about that. They're not anything that we need for our purposes to go into any depth on because in computer science we're mostly concerned with not the circuitry of the processor, even though I thought it was useful just to get everyone oriented to it, but what the circuits are actually built to do, which is execute instructions, and that's where we come into play in computer science. So Amber Wolf asked, are we going to go over things like word and double word? And we will do that today. In fact, I've got those terms. They spill over on the screen, but I have those terms in my notes here. Let me just fix that one. So we will be talking about those things today. So I will just sort of, what this class is about is computer scientists, and some of you maybe are computer engineers, gaining some insight into what's actually happening. Like when I write C++ code, ultimately what actually happens. So of course, ultimately, I don't know if it's of course, but we take our C++ code or our Go language code or whatever HLA code, we compile that, and in the process of compiling it, we translate it into a set of low-level instructions that the processor was actually designed to execute. And ultimately, those low-level instructions, which can be human read, you'll see that in our programming work. Ultimately, those low-level instructions have to be translated into binary code, which is basically zeros and ones, pure digital information, so that they can be fed into the computer, and then the processor in the computer can execute them. So that's kind of what we want to peel back the layer of C++ and peel back the layer of the compiler and get down and look at what those instructions actually look like, what it means when we declare a variable, how does the computer actually store and access that information, those kinds of things. So someone brought up memory and registers. So we will concern ourselves with registers. I think that's next week. So we'll talk in depth about those next week. But I can I'll build just the quick sketch of the way the whole thing works, and then we'll bring ourselves back to what we want to do today, which is number systems, and then we'll talk about why do we care about number systems. So so you write a high-level language program, you compile it, which means it has to be translated into the processor's instructions, which are then converted into their pure digital form, their binary form, and stored on the computer. So when you launch a program, when you run an executable or double-click a program on your computer, the code for that, the binary of that executable is loaded into your computer's RAM. That we don't need to go into the details. It's loaded into RAM. Hopefully everyone knows that the basic components are hard drive for long-term storage, RAM for working memory, and then the processor that actually does the execution of the instructions that it's being given. And we're in this course concerned with the processor itself. So anyway, when you run an executable, its code is loaded into working memory, RAM, and then it's fetched and executed by the processor. And the processor keeps fetching and executing instructions until it either runs out of instructions to execute, or you interrupt the execution of those instructions by exiting the program. I guess those would be the main ways that happens. So that's a high-level view with more of the working parts than computer scientists really need to worry about tons. We do worry about working memory because even though we work on modern computers that have huge amounts of RAM, relatively speaking, we can still write better code that is less wasteful of that RAM so that we are not causing the computer to use resources that it shouldn't need to use. So that should be a goal for us in our programming work, is to be efficient in terms of what we're asking of the computer's memory, storage, and processing resources. This is super important for people who work on embedded systems, like the sensor systems in a modern automobile or even on a modern game console. People have to concern themselves with efficient use of the console's resources because there's only so much resources to be had. So they need to be used efficiently so that they do their job well. Okay. So someone asked about the bus. So now if we shift our focus and kind of zoom in on the processor, if you haven't, you can go look at like electron microscope scans of modern processors. The circuitry inside of them is so small that you can't see the processor's circuits with the naked eye. You need something like an electron microscope to do it. But what you have to imagine on a modern processor, which is usually no bigger than maybe something like this Post-it here, is that it's filled with millions upon millions of tiny little electronic circuits. And those circuits are connected by wires. I mean, they're tiny, but they're connected by wires effectively that allows the flow of information between them. Information at the level of the processor is simply the flow of electricity. Um, and engineers concern themselves with these kinds of things. Computer scientists a lot less so. But the flow of electricity through those circuits across those wires. So the wires that electricity flows across to connect those circuits on the processor, that's a bus. So a bus is simply a wire is a simple way to think of it that connects two circuits and electricity flows between them. So you read a little bit about the von Neumann architecture, which is one way of wiring up the circuits in a processor. And the way they do that in a von Neumann based design CPU is that there's a single bus across which the instructions for the processor to execute and the data also flow across one bus, one set of wires, which means that on a von Neumann processor, the computer, if it's fetching data, it cannot at the same time execute an instruction. So it has to wait for the data to arrive before it can then go grab an instruction across that same bus and then execute it on the data that previously flowed across the bus. So that's what Intel processors use. That's what x86, which is the sort of most famous family of Intel designed processors, are built using the von Neumann design, which has one set of wires for both data and instructions. And then you may or may not, hopefully you did come across the idea of the von Neumann bottleneck. But the downside to that design is that the processor can only be doing one thing at a time. It can be executing an instruction or it can be fetching more data. And that's a bottleneck in terms of the processor's ability to perform its work. Because sometimes it is in the middle of grabbing data and it can't also at the same time be executing an instruction. So there's a whole family of modern, and Intel makes modern processors, but the sort of current wave is represented by processors like ARM. So if you're on a Mac and it's an M1 Mac, then that probably is a different kind of processor design. But if you look at your cell phone, if you look at a lot of smaller devices, embedded devices like the sensor systems in an automobile, they are running on processors that use a design that separates the sets of wires that transfer instructions and data. So they can actually move instructions and data simultaneously. They don't have the same bottleneck, which in theory means that they can have a higher performance, at least depending on the kinds of work that they're doing. So if all that sounds like this seems like more than a computer scientist needs to know, that's true. That is more than a computer scientist needs to know. Computer engineers, you're going to get your fill of all that kind of stuff. So that's all just so that you've been exposed to it in your life. And at some point in the future, if someone says, what kind of a processor is in your computer? And you say it's an x86 processor, then everybody knows that you're talking about one of the line of processors designed by Intel Corporation. And if they say something like, well, it's an ARM processor, then they know it's something different and it has a different design underlying it. And for us programmers, that usually doesn't matter very much. Like none of that stuff matters. Yeah, so Magenta asks if you have a von Neumann design for your processor, do they optimize the transfer of data and other things to make those processors run faster? And the answer is yes. So engineers do work with that design, and also compiler designers actually make it so that the sort of flow of information and instructions is optimized as best it can be. And then again, for our purposes, it's getting a little deeper than we need to go, but all of these things involve various kinds of engineering trade-offs. So the von Neumann design is simpler to execute, which probably means that in some ways it can be cheaper to manufacture, easier for engineers to do design work around, and maybe harder for people who are trying to optimize the flow of information and instructions. And then if you go with like the ARM design, which we call the Harvard architecture, then you have more complex circuitry that you have to work with as an engineer, but maybe there's more options for optimizing the flow of information. So it's all trade-offs. Oh, that's a good question. So AMD, they manufacture Intel processors is mainly what they do. So AMD will basically pay the Intel Corporation a license for the design of their processors, and then AMD will take and use those designs to actually manufacture physical processors. That's true in the ARM world, ARM as well. So the ARM company, they don't make processors, they design processors, and then they sell the designs to companies that actually manufacture the CPU hardware. I believe that the M1 is an ARM design-based processor, but I think it's been customized by Apple, and they call it Apple Silicon, is the story of the M1. But I think that more or less they are native ARM design processors, yeah. So if it can be pretty interesting. I mean, there's, um, the engineer types, when they're thinking about these microscopic little circuits that they put together, really get into digging down into the weeds with that stuff. And to a certain extent, computer scientists can get themselves involved in some of that low level kinds of stuff. Yeah, I agree. It is interesting to just have a little bit of peek into what's going on in that processor. So if you wanted a takeaway about all this, there are different processor designs. There are different ways of actually wiring together the components in the way that you design the components to be wired together. And then people buy the designs and they manufacture the processors, and then they build products around them, like watches and phones and desktop and laptop computers and the like. There's all sorts of other issues, by the way, that are beyond our scope, but the design of a processor can determine how much electricity is required for it to run. So there are processor designs that are meant to minimize the amount of electricity that they burn, which is good if you have a battery-driven product, as an example. You want to burn less electricity than more to keep the battery life longer. It's pretty interesting, actually, what engineers have done in the world of processing. Okay, so hopefully that helped a little bit. Our layer kind of starts, so our layer as computer scientists starts at the instruction layer. So a processor is designed to execute a particular set of instructions. We actually call it the instruction set of the processor. And when we use the word architecture, we often, when we're talking about a processor, when we talk about an architecture, we're actually, as computer scientists, talking about the specific set of instructions that processor was designed to execute. And there are different kinds of processors. So a processor that's designed to work with, let's say, video data will have different instructions designed into it than a processor that is meant for general purpose use, like our desktops and our phones, really. And then you have processors that do things like take digital information from a streaming music service or a CD-ROM. There are chips that are designed to convert that digital information into analog information, so it can be like played over speakers as music. And that can affect the instructions that the designers imagined, and then the CPU design that was made to execute those instructions. It's a lot of stuff, isn't it? So none of that. If that stuff is interesting, then that's wonderful, and there's a lot more you could dig into. If it feels a little bit like this is getting over our heads, don't worry about it. Um, this class, you'll find that we orient ourselves to what are those instructions that our processor, the x86, executes. What do they look like when we turn them into high level language? And also, how is data stored and represented by the processor? And then how does that interact with the software and instructions that we write? Oh, yeah. So Magenta asks, why do older processors can't always handle newer software? Um, Sometimes it's because new instructions have been added and the software has actually been compiled to a certain instruction set that the older processor didn't do. So in the family tree of Intel x86 processors, every processor is backward compatible going back to the early days. So if you get the latest Intel processor, it will have all of the instructions of the last generation of Intel processors, so that old software will run on new processors, but it doesn't always work in reverse. So if I make software for the latest Intel processor with the latest instruction set, and I'm using those instructions, an older processor won't have those instructions, won't be able to execute them. That's sort of one simple example of why processors and software wouldn't be compatible with each other. Another reason is the way data is stored and accessed by processors. So you may or may not all be aware of the idea of the 64-bit processor, which is pretty much all the processors anymore. But when we say a 64-bit processor, that determines how much memory the processor can actually have store addresses for. And 64 bits of an address is a lot more memory addressable than 32 bits of address. It's kind of akin to saying if I have a phone book with 10 pages, how many people's addresses can I write in it? Versus a phone book with 1,000 pages, and how many addresses can I write in it? A lot more. Which means that my old address book, while I can accommodate all of it in my new bigger address book, it won't work in reverse. So that's another reason why processors can be incompatible with each other, is the amount of data that they use to address memory and what their capacities are in terms of storing information. Because a 64-bit processor can store much bigger integers at their maximum than a 32-bit processor, which can store a much smaller range of integers at their maximum. Okay, so again, it's a lot of stuff, but it is kind of interesting stuff. Yeah, that's a good question. So, Adeline asks, why do the number of bits always seem to double themselves? Um, and there's actually no reason why it has to be that way. But because binary information which is how we represent information to computers, is powers of two, then things just tend to look like powers of two everywhere. Technically, it doesn't have to be that way, but that is the way it tends to work out, is that we just add another column of power of two, and get sort of, well, typically more than twice the space. But that's why it does that. Even though it doesn't have to, it just seems to have become kind of the rule that we follow, is that we do powers of two, um, or things that look like they're doubling. Okay, but we'll get to that. We can see examples of that when we deal with binary today. Okay, so I'm going to get to the, I'm going to walk through the module and then show you what I hope is a desirable improvement to the labs. So I'm on the course homepage, and I just start here to remind you that most of the time, if you're looking for something, I hope you can find it here. So where I'm at and how to find me. Usually your view of the course homepage, I think, will have a to-do list for you or something like that that reminds you of soon to be assignments. And then the schedule at the bottom, where you can week by week access the week's content. So I am going to step through the week 2 module And then I'm going to switch over to my virtual machine for doing the rest of the class. But let's just quickly review the module and remind you what's going on this week. So the goals for the week is kind of where I was telling you that it's going to feel like two separate lanes for a bit until we bring them back together. But they do work together. It just won't necessarily feel exactly like that today. So we're going to look at numbering systems and how they work. This is one of the biggest deals in this class, in my opinion, is that you have some basic literacy in number systems. If you understand how number systems work, there's a tremendous amount of power in it in terms of representing information. And it will also open up to you the ability to read things at high and low levels in computer science and computer engineering that will make sense to you that might not make sense to you otherwise. So in particular, getting comfortable with what hexadecimal is trying to say, what it means when you look at it. You'll see a lot of it once you learned it's out there, and then you'll realize, oh, that's hex, and that's hex, and oh, that's hex too. Everything seems to be in hexadecimal when I'm looking kind of at the low-level data in the computer, and there's a reason for that. So we'll look at binary, decimal, and hexadecimal. Those are the ones we need in this class. Another common one is octal, which is a base 8 system. We don't need it, but if you know how any numbering system works, then you can figure out any of them. So if you're curious about it, you could go poke around with the octal system and you'll realize that the same rules apply, and you'll be quickly able to figure out an octal value, just as you would a binary, decimal, or hex from this class. And then we'll have the other, what feels like a separate lane, which is to continue to get ourselves ramped up quickly into doing some basic HLA programming. For the most part, we're going to do high-level programming for now, but as soon as we start doing arithmetic, then we're going to have to start using assembly instructions, and that's, for me anyway, something to look forward to because it's fun. It feels good to get down beneath the level of to a lower level than the high-level languages typically have you go. Okay, so some readings. That will just back up kind of what we're talking about. The Hello World, hopefully everyone has figured out that you can be selective in your reading. There's a whole bunch of content on installing high-level assembly language on your computer, but I've already given you a computer with it installed, so you don't really need any of that information. It's the stuff that happens after that we're interested in. And then data representation, which probably is going to overlap a lot of what I say, but a slightly different presentation of this information that we'll go through today. So it may help some people understand how these number systems work. What did I change about the quiz? Oh yeah, there was a question in the quiz where I left 2 blank possible answers because I didn't need them and I forgot to delete them. So I went and deleted them, and I don't think it'll affect anybody's quiz because all I did is I removed 2 non-answer answers from one of the questions. They were literally just blanks sitting there looking weird. Oh, I didn't realize it needed to be saved. Okay, so the lab, and here's the change I've made to all the labs, is I've put links to the language reference and the standard library reference on every lab. Someone brought up that question last week, like where are the links to that stuff? And I got to thinking about it. I thought, well, I just put it in all the labs. That's the place where it would be. And I'll also put it in the projects, which would be the places that it seems it would be most useful. Yeah, so Amber Wolf said there's one of those empty answers on the first quiz, and I think I had been notified of that, and maybe I deleted it, but thanks for reminding me. I want to go get that out of there just because it bothers me that it exists. Okay, so hopefully we have time before I have to quit the live stream to get started. I don't see a problem with getting started on the second lab. So the discussion this week, so Week 2 filter, I think in this class no one had a problem with that. Some other classes had a problem using these filters to find the discussion. But anyway, this is um, encouraging all of you to go out and sort of find extra resources to help people understand these number systems. I think that they're an important part of what you should want to get from a class like this, is that you know how binary and hexadecimal work. You may not be a pro at doing binary arithmetic or hexadecimal arithmetic, but you will at least have a sense of how the numbering systems work and how they're used to represent information. So the discussion will be asking you to go and do some quick research and see if you can find some interesting way of learning or an interesting presentation of one or both of these numbering systems to share with the rest of the class. And then the last thing is the reminders. The individual project is pretty far down the road, but I would encourage you to go look at it sooner than later so that you know what to expect of it. I don't think I'm going to have time to look at it today, but in the next couple of weeks, I will stop and kind of go read through it during the live stream. But anyway, it's linked here just to remind you that that's out there and it is ready for you to look at it whenever you are ready to look at it. And it's ready for you to start it whenever you are ready to start it. Someone says they have no sound. Yeah, it must be on your end, Linkridge, because as far as I can tell, I've still got good sound. Okay, yeah, and other people have sound, I think. Okay, yeah, so the problem must be on the far end. Okay, so let me switch to the virtual machine, and I'll just use it. Where is it? Okay, so let me switch to the virtual machine, and I will use it to go through the content today. So we're going to talk about these numbering systems. We're going to talk about the way the Intel processor organizes data. We'll look at some tools, and these tools are available not just in Xubuntu, but you'll find them on your Mac and your Windows systems if you look. And then finally, we'll look at some HLA programming concepts, which are a little bit connected, but won't feel fully connected until I think next week. So let me get my virtual machine woken up. The reason why we're using a virtual machine is because there's no way I could possibly help each individual in the class install the HLA software, and it's more complicated than regular computer users know how to handle. So I wanted to eliminate the entire problem of people spending several weeks of the semester saying, I don't know how to install this slightly more complex piece of software, so I just installed it for them. I also think, which I think I talked about last week, but it's a good question. I also think that people should be exposed to the Linux system as programmers, especially as engineers and computer scientists. So I hope that you take advantage of this sort of pre-built system and pre-installed with our tooling to poke around the Linux system a little bit. So yeah, I did it because from experience, I know that most people in the class would struggle with installing the tooling for our programming language. And being in an online class, there was just not going to be any way I was going to be able to manage getting 60 people through their installations. A few of you, so if you already know Linux and can use Linux, you can install it. But if you're sort of a regular Windows user or a regular Mac user, you'd struggle to install it like as not, in my experience. Okay, so I'm going to, actually, right now I don't need to do any programming. Let's just talk about the numbering systems. So let me get myself just a regular text editor. Do I have a regular text editor, or am I going to have to use... Yeah, I'll just use Visual Studio Code. Okay, so I'm typing something because I don't want to look at that that stuff from VS Code anymore. All right, so number systems. So I'm going to write down sort of the basics of them and then kind of go through a couple of examples of how they work. So don't bother me. So let's start with the decimal system. So why do we have the decimal system in this class? It's because it's the one that you and I are most familiar with. We just intuit how the decimal system works, even though a lot of you, it may have been a while since you've thought about how it actually works as a system of representing information. But the decimal system is here, and it is always going to be here because it is a point of reference for us. It is our home in terms of how we represent numbers, and we're all very familiar with it. So we keep it there because we're familiar with it and we're comfortable with it, and we will never stop using it as far as I know. So that's why the decimal system is being talked about in this class. It's also so that you understand how numbering systems work, that they all work the same way. But it's also going to be our point of reference because we're familiar with it. So the what of it is it's a base 10 system. That's what we would call it, a base 10. It leans on representing values in powers of 10. So decimal, base 10, powers of 10. And it uses 10 symbols to represent it, or we use 10 symbols to represent it. So notice decimal, which means 10, is base 10, powers of 10, 10 symbols that we use to represent it. 10, 10, 10, which is useful to remember because we're going to do a base 2, 2, 2, 2, and a base 16, 16, 16, 16. And the rules are all going to be the same. It's just when you apply the rules, it takes some getting used to. So 10, 10, 10. So if we have a number like 4, what does that really mean? Oh, I should put this also. So this is so what I mean by this in plain text is 10 to the power of 0. So when we look at a base 10 number, a decimal number, the rightmost digit is some amount of 10 to the 0. So for example, if we have the digit 4, because it's only one digit, it is by its nature already the rightmost digit. But another way to write this is I'll do it this way to try to keep them easier to read. Another way of saying what that digit 4 represents is that is 4 of 10 to the power of 0. So we have 4 multiplied by 10 to the power of 0 is what that actually represents. Now, because this is decimal, you just kind of intuit what 4 means for fingers, for apples, for cars, for birds, whatever it is. You kind of have a sense of what we mean when we say that. But if we're being more formal about it, that's 4 there means that we're looking at a base 10 number that is 4 times 10 to the power of 0. Let's get another one, like 24. Keep those lined up. So what does 24 mean? Well, if we start at the rightmost digit, that's still a 4 times 10 to the power of 0. And I'm going to go backwards to the left. So as we go to the left, the 2 is the next digit. And what we're told is we go up by 1 power as we go to the left. So what we have there is 2 times 10 to the power of 1. Yeah, good point, Magenta. So if you remember that any value raised to the power of 0 is 1. So 2 to the 0 is 1, and 3 to the 0 is 1, and 4 to the 0 is 1, and 5 to the 0 is 1. I'm glad Magenta brought that up because you're going to want that piece of information. Any number raised to the power of 0 is 1. So what I'm doing here is I am breaking these values down in terms of what they mean in the decimal numbering system. So what we call 24 is actually in the decimal system 2 of 10 to the firsts, because it's 1 over from 0, and 4 of 10 to the zeros, which is another way of saying 20 plus 4, because 2 times 10 to the first is 2 times 10, which is 20, plus 4, which is another way of saying 24. I'll finish this one as well. I'm not sure how long I can keep those things lined up before I make a big mess of it. So let's do one more. So if we do 524, and I'm going to start from the rightmost and then kind of go backwards back to the left. So I still have 4 as the rightmost digit. So that's 4 times 10 to the 0th power, which is 4 times 1. And then if we move to the left, we get 2 times 10 to the first power. So every time we go to the left, we raise the power by 1. So we start at 0, we go to 1, 2, 3, 4, 5, 6, 7. So we get 2 of 10 to the first, and then we have to go over left from there to get the 5. So that's 5 of 10 to the power of 2. So you notice how the powers of 10 start at 0 on the rightmost, then go up to 1, then go up to 2, and they go up by 1 every time we shift left to a new column, which is another way of saying 5 times 10 squared is 5 times 100, which is 500, plus 2 times 10 to the first, which is 2 times 10, which is 20, plus 4 times 10 to the 0th, which is 4 times 1, which is 4, which is another way of saying 524. So that's a system that... Oh, wait, let me see how I can line these up. Why I want to line them up is because it would mess with my sense of order if I didn't. So that's how the base 10 system works, and it may have been a while since you've actually sort of thought of it that way, but that's how it works. And in my opinion, it can be useful to practice this. Let me save this real quick. I shall call it, today's Tuesday, the 30th. Okay. Anyway, it's useful to practice this sort of how does the decimal system function. If you haven't thought about this in a while, just because it gets you warmed up on the whole idea. And of course, if I had added another column like 1,524, I would have 1 times 10 cubed, which is 1 times 1,000, which is 1,000, plus 5 times 10 squared, which is 5 times 100, which is 500, plus 2 times 10 to the first, which is 20, plus 4 times 10 to the 0. That's how that numbering system works. Okay, so now let's look at how these things function in these other numbering systems. The other numbering systems work the same way, except for the base. And the base drives the rest of the system. Hold on just a moment. So I just try to block the ones that aren't in our class. Okay, so the binary system. Why the binary system? So do you guys know why the binary system? Does anyone in chat know? Why don't we just do everything in decimal? That's the one we're familiar with. Why bother? That's true, Druid. So that's the way it works. But why binary? There's a reason why binary comes up. That's also so. Yeah. So Evan, you're on to something with the logic gates. And Druid is also correct about high and low voltage. So state that more simply. So I'll give you a hint. As computer scientists, why is binary something we should be familiar with? Right. So someone said it without using the word. It's because computers communicate in binary for all intents and purposes. So computers communicate and move and store data as electricity, and electricity, you can think of it as just sort of there being electricity or not being electricity, even though technically on a computer it's actually a high voltage circuit versus a low voltage circuit. But either way, the reason why binary is because that's how we represent information to the computer. And that's how the computer stores information. So the why of binary is because that's the computer's sort of native numbering system. And in fact, that's the computer's only way of storing information when it comes down to it. Is in binary. And it is related to the fact that we're talking about electronic computers that run on electricity with voltages, which you can simplify it in your mind to say circuit on, circuit off, like a light switch, but technically it's circuit in high voltage state versus circuit in low voltage state. And yeah, there are other implications about that as well. So for humans, we think of the binary system as something we represent as ones and zeros, although technically inside the computer, it's really just electricity, electrons. Okay, so binary. So that's the why of it, is because we want to know more about how the computer thinks in terms of the information that it stores and represents. So what is binary? It's a base 2 system. So watch how this happens. It is constructed on powers of 2, and it uses 2 symbols. And someone already got that. Where did that go? Druid already said the 2 symbols are 0 and 1. The symbols that we use to represent binary don't have to be 0 and 1. It's just it's what engineers defaulted to at some point. The symbols are in some ways just symbols, but we use zeros and ones when we want to represent binary for our own consumption, and in a way for the computer's consumption as well. So 2 symbols so then we'll say the rightmost is 2 to the power of 0. Go up by 1 as we move left. So let me stretch this out so I don't fall off the screen as quickly. Okay. So all we have to do is use the same functionality of the base 10 system, but do it in powers of 2 with 2 symbols instead. That's true. So Evan asked, are ASCII symbols in binary ultimately? So often if you look at a binary, an ASCII table, you'll see decimal and hexadecimal representations. But it is true that ASCII ultimately is talking about a binary representation of of characters. That's true. Okay, so here we go with some examples of binary. So this one's trickier because what we're going to do is we're going to translate the binary into decimal. Why are we going to do that? Simply so that we can make some sense of what we're looking at. So what you'll see me do with the binary system and the hexadecimal system is often convert it into decimal so that I understand it better and so that you understand it better. So you're going to see me in this class prefix all the binary values with the percent sign. So I've typed a percent sign here is because I'm about to type a binary value. There's two reasons to do that. One reason is because that's how the HLA language lets you type binary into your programs. But it's also because we want to be clear what our meaning is when we put values down on screen or paper. So if you see a percent sign in front of zeros and ones, that thing is a binary in this class. Yes. So Druid asks, is it standard to use 4 bits to indicate a value? And it is. And you'll see that in a second. There's a really cool thing that binary and hex do when they work together that those 4 digits allow to have happen. So I'll keep that in mind, Drew, because that's a good point. It is standard to do at a minimum 4 digits, although I'm going to start with a single digit of binary. In fact, I'm going to start with this digit of binary. By the way, if you see a value somewhere that has anything other than zeros or ones, it can't be binary. It has to be something else. But in this class, we will be careful to always put a percent sign as a prefix to our binary values. When we're coding an HLA, that's because that's how HLA requires it. And for our purposes, so we always are on the same page in terms of what is this thing. If it has a percent sign, it's a binary. So let's just start with a single bit, a 1-bit value. So that's a 1-bit binary value. And what it means in terms of the system is, and now we're about to do a decimal translation so that we understand it better. So to do a decimal translation, we're going to say that's 1 of 2 to the 0. And as we just established with the decimal system, any number raised to the 0th power is 1. So that's the same thing as 1 times 1, which is, of course, 1. So notice this 1 down here, I wrote without the percent sign. That means that's a decimal. So binary 1 is the same thing as decimal 1. And the reason why we did the to decimal translation is so that we have a little bit better understanding of what this thing means. All right, now let's do a bigger one, and let's do it in this size. So we're going to do a bigger one now. I'm giving up on the keeping things lined up because I'm just going to use up all the class time on it if I keep doing that. Okay. So, but I am going to start at the rightmost digit and work my way backwards. So there's the percent sign. That's telling us in our class, this is a binary number. The other clue, of course, is that it's only ones and zeros being used to represent it. So that would legally be a binary number. And then for sure it's a binary number because it has the percent sign as a prefix on it. So this is a 4-digit binary number. By the way, this is what a nibble is a 4-digit binary number. A bit is a 1-digit binary. A nibble is 4 digits. So going from right to left, so we'll start on the rightmost, which is this 1 here, which would be 1 times 2 to the power of 0. And now if I start working my way back to the left, which I can't do for some reason. There we go. My fingers were betraying me. So this next one to the left is the 2 to the first column, and I have 1 of those. So I have 1 times 2 to the first. And if I go left again, I get to the 2 squared column. So I have 0 of 2 squareds. And if I go to the left for the last digit, I have 1 of 2 cubed column. Oh, that wrapped. Okay, so let's drop that down, put it here. So we're doing a to decimal translation again, just to understand it better. So what does that all look like? Well, that's 1 of 2 cubed is 1 times 8, which is 8, plus 0 times 2 squared, which is 0 times 4, which is 0, plus 1 times 2 to the first, which is 1 times 2, which is 2, plus 1 times 2 to the 0th, which is 1 times 1, which is 1, which means that the decimal presentation of this same information is 11. So this nibble, binary 1011, is decimal 11. They are the same value, the same quantity, or the same information, whatever that information is. So binary 1011 is decimal 11, which is what I did that translation for. Watching the time a little bit. I think I'm doing okay. If I go a little bit long, I'm going to end up taking a break somewhere. Okay, so let's do one more example of how the system works. I'm going to do a longer one now. And you're going to see me use some HLA notation. And all I really mean by that is I'm going to do this. So I'm going to do 0, 1, 1, 0. And then I'm going to use an underscore to separate that out from the next grouping. So this time I will do 0, 1, 0, 0 and just kind of reverse it. So before we translate it, before we do a to decimal translation, it is a byte. Good one, Evan. So Evan points out in chat that we now have a byte, a B-Y-T-E byte. We know it's a decimal, a binary. Whoops. We know it's a binary because of the percent sign, and also because there's only zeros and ones being used to represent it. We have 2 groupings of 4 separated by an underscore. So in our class, this is how we're going to do binary numbers. We are going to use underscores to separate groups of 4. Does anyone remember what the one grouping of 4 is called in chat? That's a nibble. All right, good one. Good one, y'all. So yeah, add-on in Xanadu is nom got nibble. So isn't this cute? What is 2 nibbles? It's a byte. Isn't that cute? I think that's on purpose, by the way. I think somebody was being cute at some point. And thought, well, 2 nibbles would be a byte, wouldn't it? So yeah, it's kind of funny, I think. And yeah, I don't know. I think they did it on purpose to be cute. At least I hope they did, because that would be a way better story than it being an accident. Okay, so let's do a to decimal translation. And again, we do that to practice how the system works, and also just because we understand decimal better. So what does binary 0110 0100 actually mean? A megabyte would be 1,000 bytes, which would be 2,000 nibbles, right? Yeah, so a bit is just 1 digit. So a 0 is a bit and a 1 is a bit. So a nibble is 4 bits and a byte is 8 bits. So one binary digit is a bit, and a nibble has 4 bits in it, and a byte has 8 bits in it or 2 nibbles. Which is starting to sound a little weird as I say that, so I'm going to stop saying that for a little bit. Okay, so let's do the translation on this thing. I'm going to go from right to left, even though it's kind of a huge pain in the rear. No, you know what? Let's just go from left to right. We can do this. And it'll go faster. So if I figure out what my powers of 2 are, if I get to the far left, so 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. So that leftmost is 2 to the 7th, and I don't have any 2 to the 7th, so I'm going to leave that one behind. I do have a 2 to the 6th, and I have one of those. That's this one way down here is a 2 to the 6th. I also have a 2 to the 5th. I don't have a 2 to the 4th. I don't have a 2 cubed. I do have a 2 squared. I don't have a 2 to the 1st, and I don't have a 2 to the 0th. So once you have a little bit of practice, you can easily go from left to right. You just sort of count your way over what powers is the column, 2 to the what, and then work your way back from left to right. All right, so what does that number mean? So that is, what is 2 to the 6th? 2 to the 4th is 16, 5th is 32, 6th is 64. So that is 1 times 64, which is 64, plus 1 times 32, which is 32, plus 1 times 4, which is 4, which is in decimal, that's 100. Right? 96 plus 4 is 100. Yeah. So that's decimal 100, that binary. All right, that's the binary system. Let's do the hex, and then we'll do sort of the organization part, which is bits, bytes, nibbles, words, all that. What does all that stuff mean? But let's get this last numbering system down. I'm going to move this up. So let's do hexadecimal. The Y of hex is because it's shorthand for binary, and I will show you how that works in just a bit. But the reason why we do hex is because it actually is a way to do binary in shorthand. And it's a very easy way of doing binary in shorthand, so that is why it is here. Computers represent their information in binary for all intents and purposes. We, on the engineering side of things and the computer science side of things, use hexadecimal often because it is a way to represent binary in shorthand, in much more compressed fashion. You can tell, by the way, if you look at this binary 100 versus decimal 100, that as you decimal allows you to represent information in a more compressed format than binary. Notice how binary is a lot more digits and decimal is less digits. Hex is even less digits than that. So hexadecimal will allow us to compress our kind of what we type on the screen or write on paper even further. But the why of it is because it is shorthand for binary. And it becomes kind of the native way that we represent binary for ourselves because it's just faster and smaller to write. Okay, so what is it? It's base 16, which can be kind of nasty. That means that the columns are powers of 16. That means that there are 16 symbols to represent it. Does anyone know what the other 6 are? Once we run out of the numbers, what are the other 6 that are hex? Somebody probably knows in chat. Nice one, Druid. Yeah, good one. So A, B, C, D, E, F. So that's how we get 16 symbols to represent the hexadecimal system, as we simply add some letters. That's kind of fun because you can actually make hex values that spell words, and you can kind of play around with that a little bit. Like the word beef is hex digits. Anyway, so now let's look at how it works. In HLA, we are going to do hex digits with dollar signs for the same reasons that we do binary and percent. The HLA language lets you write hex values into your code with a dollar sign as a prefix. And it is also a reminder to us that the information we're looking at is hex if it has a dollar sign in front of it. So we will always do that in this class. Percent in front of binary, dollar sign in front of hex, nothing in front of decimal. So if you just see digits, that's decimal. If you see a dollar sign in front of it, that's going to be hex. If you see a percent in front of it, that's going to be binary. So let's do an easy one, and then we'll do a couple of harder ones. So $3, the hex value, we are going to do a to decimal translation of it. And again, we do that because it just helps us understand what we're looking at. So if we start at, I didn't do the rightmost. Rightmost is 16 to the power of 0. Go up by 1 as we move left. Yeah, so Adeline asks, could we in theory like ditch all of our decimals and write things in hex or binary in our regular programming languages? Hex, yes. As far as I've seen, every language that I've worked with will allow you to, some of them use different symbols. They don't necessarily all use the dollar sign, but every language I've worked with will allow you to put hex, raw literal values in instead of decimal. Some languages will let you put octal and binary, but not all languages will let you do literal values in other numbering systems, but hex for sure. Okay, so there's a question about if we can compress by going to further bases. Well, as a practicality, if we were to go to base 32, what would we use to represent the extra digits? So I think one of the limiting factors is simply that sort of our standard set of characters from the Western world isn't big enough. Well, we could get to base 32, and maybe someday that would happen. But I think just for now, there's been no reason that anyone's seen as to a super big need for that, although that's not saying that someday it couldn't happen. But part of it would be that we'd start to run out of sort of the common characters, at least in the Western world, if we got too big. Okay, so this 3 in hex is rightmost, which means we're looking at 3 times 16 to the 0 power. And that's simply 3 times 1, because everything to the 0 power is 1. So 3 times 1 is 3 in decimal. And notice I didn't put a symbol in front of it because now we are looking at decimal. Yeah, or, there's a lot of alphabets that we could use to get to bigger numbering systems if we wanted. Okay, so now let's do this one, so that you understand what these characters mean. So $A to decimal translation. So in decimal, the A means 10 of. So when we sort of do a translation, either on paper or in our heads, to decimal, the A means 10 of, the B means 11 of, the C means 12, the D 13, the E 14, the F 15 of, when we are thinking of translating to decimal. So the $A there means 10 of 16 to the power of 0, which is 10 times 1, which is decimal 10, is what that means. So now let's do some bigger ones. Let's go to E. And we'll do a to decimal translation. Again, just for the purposes of understanding a little bit better what in the heck's going on. Now I'm going to go left to right this time because it's not too many columns for me to figure out on the fly. So if we start at the leftmost, well, we're only one over from the 16 to the 0 column. So that would be, I'm going to move this up now. So this is the 16 to the first column. So that is 2 times 16 to the first. And then as we work our way back down to the right, we have E, which in decimal is 14 of 16 to the 0. And then I will drop down to keep going. So that is 2 times 16, which is 32, plus 14 times 1, which is 14, which is 46. Decimal 46. So 2e hex is decimal 46. And then let's do one semi-nasty-ish one before I bring up the calculator and cheat. In fact, I'm going to do a nasty one and bring up the calculator and cheat. So let's do a 4-digit one. You can spell words, which is kind of fun. Okay, so FACE. What that's going to be, I'm just going to say it. I'm not going to write it because now we're going to bring a tool in to help ourselves. So 16 to the 0, 16 to the first, 16 squared, 16 cubed. Yeah, we do, Adolin. So Adolin makes a good observation that we just take it for granted that decimal comes so easily to us. When it is, in fact, a system that works like this, it just becomes so native to us that we don't even think about it. So that's a good observation, I think, Adolin, that how much we take decimal for granted. Okay, so FACE would be in decimal 15 times 16 cubed, which is a huge number, 10 times 16 squared, 12 times 16 to the first, and 14 times 16 to the 0. That's starting to get a little big for my taste. So let's do, hopefully we're going to find this on our system. Let's go find the calculator on our Ubuntu system. Oh man, is there no calculator? We're going to have to install one? We're going to have to install one, aren't we? We are going to have to install one. We'll get a bonus round. I'm going to do it in Linux, but you can do the same thing with your Mac calculator or your Windows calculator. But we need a bonus round. So I'm going to bring up the terminal emulator. And I'm going to do this on the Windows side after I do it in Linux. So if you want this in Linux, let's do that. So there's a question, could I do this in the terminal? If I install the terminal calculator, which is called BC, I could do it. So you can type all these commands if you want to. I want a calculator. I don't want a command line calculator. I just want a nice little calculator. You don't need to worry about this part. I'm going to make a choice for us. Calc. I wonder if that's going to be a GUI-based thing or not. Well, let's find out. So if you are following along and you want this, and I'll show you how to do it in Windows if you don't want this, we're going to say sudo apt install calc. So we need to install the calculator program. Our password is student, S-T-U-D-E-N-T. It's going to want to download and install some things, so I'm going to let it. I didn't notice it didn't have a calculator when I put these images together. Let's see if it's in here now. Oh, it's a command line calculator. That's nasty. Okay, we don't want that. We do not want that. So let's say no to that. No, so Evan asked, is Xubuntu my distro? No, I have a free BSD laptop and I have just a standard Ubuntu laptop is my main computer. Um, so I may upload a new version of well, I don't want you to have to go through that. What I want is an X-Face calculator. And I'm going to go figure out what it is and then put it on here. How do I get the calculator? I'm looking up something on the side so that you don't have to watch all the mess. Calculator or Xcalc. Let's try Xcalc. So we're going to say sudo apt install Xcalc. Nope. That one don't work. Let's try calculator. Okay, that one did come in. So if you're following along, let me clear and I'll just present to you the command. So I just typed this command to get myself a calculator installed on my Xubuntu system. And let's see if it's now here. There it is. Calculator. Okay. I'm going to show you the same thing on Windows. So if this is all sort of getting past, yeah, so calculator is the GNOME calculator. But if this is getting past what you want to do, I'm about to show you in Windows the same thing. And Mac would be very similar. So what we want is, let's see if the scientific mode, do we get programmer mode? Aha! So let's go to basic mode. We're going to change, oh wait, you have to be in scientific mode to get different number bases. So we can bring up this hexadecimal number base and type in FACE. And I'll show you in Windows also. This is not my favorite GUI calculator, but it's doing the job. Anyway, FACE, and then I can go back to calculator and I can switch it to decimal and it'll translate it for me. I can also go back to calculator and switch it to binary. This says infinity. That's stupid. Oh, I could have also done this. Except for I'm not sure why it thinks that is what's paper mode? No, that's junk. So scientific mode. Anyway, you can use your calculator and get some of these things. That calculator is not just the best. So let me switch my streaming view and do it in Windows real quick. But to be honest, I don't like the Windows one very much either. So I'm going to bring up the Windows calculator. And then I'll get it on the screen where you can see it. Okay, so let me get it on the screen. Okay, so here's the Windows calculator. And what I'm trying to show you is that usually your system's calculator, although Xubuntu didn't come with one, which is a disappointment. Now I need to go figure out how to get myself one. Anyway, your Windows system and your Mac calculator will do the following. If you bring up your calculator, you can switch it to programmer mode. And then you can see, so we were in hexadecimal. So we will put face in here. And if you look on the left, you can actually see in the Windows version of the calculator, it's doing the translations on the fly. So there's hex, face, decimal 642016. There's the octal, which we're not going to use in this class. And then finally the binary. And you notice that on the Windows calculator, it separates the nibbles with spaces, which is super, super helpful. I believe if I click on, what's this do? Yeah, so if you click on this little button, you can actually manipulate the individual bits of the value. So I can take off this one way up here and change the hex and the decimal and the octal and the binary kind of manually. So your Mac calculator will have a programmer mode. Your Windows calculator will have a programmer mode. And I need to go find us one, and then I'll do a demo on installing it next time that has a more usable programmer mode than the calculator did. It has one. So I did this install, and then if I go up to the little program and I start typing in calculator, there is one. And if I am in the scientific view, I can do a little bit with the different number bases. But I think you're right. So Evan says maybe this is a 2-byte calculator, and I think you're right. Let's see if I can get more than that. Oh, you're right. Thank you. Sorry, I switched over here and started playing around with the calculator. Thank you for catching me on that, chat. So I think that's right. This is probably only a this may only be a byte sized. So I have to be careful about the values that I put into it. I switch. So what I was doing is I switched to binary mode just by clicking on the little bin here, which you can also use the calculator menu and change the base. But it'll change the base down here in the screen, and then you can type out a thing. Probably clear, so I can type like 101000101 in binary, and then I can switch to hex. That's A5 to decimal. That's 165. So this calculator, the GNOME calculator, will do within limits some of this work and help you. And the Windows had a much bigger array of values it could handle. Oh, the GNOME calculator is different. Okay, so maybe we'll try the GNOME calculator next week. Because I'm burning up tons of your time on this stuff. Gcalc. Should we just do it? Maybe we should just do it. I'm going to sudo apt install gcalc. You can all do this on your Linux system if you want to. Okay, yeah, I don't have access to it as it is right now. So there were other options. I'll go play around and see if I can find a different option. Otherwise, we'll just make do with the one that we're offered. We will actually write our own piece of software to do these conversions for us, so that might be more fun anyway. We'll write it in HLA. And then we'll use the calculator. You have to install it. So if you're watching later, this command I'm showing on the screen right now, hopefully. Yeah, you'll need to run that command. It may ask you for your password, which is student, to get the calculator. And then you'll have some limited functionality for exploring the different number systems. Okay. But Xubuntu, that's something I'll have to keep in mind. It didn't give us as much goodies as I would like. And it wasn't even that small. Okay, so now let's do some short, and this is going to be a long class today, so sorry about that. Yeah, so I know you may not be able to stick around. I apologize for that. I'm gonna go long today, so I'm gonna do one conversion from binary to hex and hex to binary, and then I'm gonna take a short break, and then I'll finish. GNOME calculator. All right, let's try it. Oh, I'm happy. Very nice. Okay, so if you're watching at home, maybe we have a usable calculator now. What's it called? It's this guy. It's just called calculator now. So now I have 3 running on my system, but I just want calculator here. Yes, this is the one that I wanted. Thank you for that, Evan. Basic programming. Sweet. Okay, so this command in the terminal, you want to run this to get this nice one. That's what I want. This is the calculator that I want. The command to install it is right here. And then you will have a good calculator, which is called calculator. Oh, and this one, see, you can switch between. So face. I can switch to the different bases. The binary is just being shown down here in this little screen, kind of like the Windows does it. Decimal. Oh, no, you have to actually change the value, right? Will it change it to hex? Oh, it's showing me down here somewhere to the right. What does this thing do? Cute. Okay, yeah, this one's better. This one is definitely better. I don't need any of that stuff. So yeah, this one has a programming mode, like the Windows calculator and the Mac calculator both have programming or programmer modes that'll let you fiddle around with bits and stuff. So I'm actually clicking on the individual bits, and it is showing me hex. So cool, thank you for that. There's the command to install the good calculator, GNOME dash calculator, and it will just be called calculator. This guy right here. And then you'll have it inside your Linux system if you want it. Hey, it came up bigger this time. Huh. Okay, one conversion and then a short break. So anyway, I was just showing you the calculator, and the Xubuntus didn't have one installed. So if you want to, the last calculator we tried in this video is GNOME calculator, and that's the best of the ones that we tried. But you can also go and open your Windows calculator or your Mac calculator, and they both have programming or programmer modes that will let you explore the number bases. There's also websites that have converters from the different bases. Okay, so let's talk about binary to hex conversions and then take a short break. Yeah, I know some of you will have to go and do other things. So yeah, thanks for being here. Sorry I'm going long today. It's gonna happen sometimes, but the video will be up as soon as I get done. I'll get the videos moved around so you can find them later. And you'll also find, if you're leaving now, that right after this, I'm gonna put the little screen thing that says "Be right back." So then you'll have that kind of as a marker to where you had to step away. Okay, so let's do a binary to hex conversion. Let's do binary to decimal first. So what we're going to do is just a quick table of conversions of just nibbles at a time, which it turns out is all you actually need. To decimal. Let's just do a big table and do it all at once. Table. Okay, so 0 in binary is 0 in decimal is 0 in hex. And hopefully you remember the symbols. So % for binary, no symbols, prefix for decimal, and then $ for hex. A nibble of binary becomes a single digit of hex. So, and then we'll just work our way up. So 0001, that nibble value in binary is 1. In decimal is 1 in hex. And then I'm just going to do a table working my way up. And I'm kind of just letting this happen. So this is kind of just an easy way to remember these basics in terms of converting between them. Now the real magic is the binary to hexadecimal conversions, but just notice that the nibble 0000 binary becomes $0 in hex. So one nibble of binary is going to become one nibble of hex. What's next? 5. 6. That'd be I only have to go up to 9, so this won't take too long. And of course, if you want to know how I'm getting these values, you do that sort of to decimal conversion. So this one is 1 times 2 to the 0. This is 1 times 2 to the first. This is 1 times 2 to the first plus 1 times 2 to the 0, and so on. Oh, in fact, I'm going to go all the way up to 15. But still, that's not very long from now. So thanks for your patience as I walk my way up. 10 is next. $11, so 1011. Because 12, so that is 8 and 4. Don't do that. It's trying to 0, 1 is 13. I'm almost there. 14 says and 15. All right, so this table can be very handy as you're kind of getting accustomed to these numbering systems, because it makes the binary, and I'm going to move that up the screen and then do some just binary to hexadecimal, and then take a break and then do the HLA part. Not table, just conversions. So here's the magic here. If I have any, like I'm going to do a huge one. So let's just say we have a binary number like this. How do I convert that to hex? I just take each nibble at a time and I replace that nibble with its hexadecimal conversion. So I'm going to go from left to right. So this nibble here, 1000, is hex 8. The next nibble is 0001, which is hex 1. The next nibble is 0101, which is hex 5. The next nibble is 1111, which is hex F. So that's what we mean by hex being a shorthand for binary. That the conversions are simple. You just nibble, 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 and you can take a very large binary number and just a nibble at a time convert it down to its hexadecimal representation. All I had to do was remember what each nibble means, how each nibble is represented as hex, and then I just take each part and assemble them as a hex value. It works the same the other direction, and then I can truly take a break and then do the programming part. So let's go the other direction now. We'll do beef. Yeah, I'll do that right after the break, Ember Wolf. So I'll do the what the sizes mean right after the break. On x86, there are 2 bytes in a word. Okay, so beef. that hex value in binary, all I have to do is nibble at a time. So I go find the binary for the B, which is 1011. And then the binary for the E, which is 1110. And then the binary for the next E, which is 1110. And then finally the binary for the F, which is 1111. And I have converted a hex value into binary. So hex and binary move back and forth between each other very quickly and easily if you have this little table at hand. Okay, so short break. I think I'm going to end up going for like 2 hours today. So apologies if you planned your day around the hour and a half. Hopefully you also need a short break. So I'm going to get up and take a short break. And then I'm going to finish with the organization part. So bit, nibble, bite, and so on. And then look quickly at the programming challenge to get you a start on that for this week's lab. So very much appreciate your patience. And if you're having the time that you're sticking it out with me, if you can't, that's okay. But it's 2:36, so I'm gonna take a break enough to take a bathroom break. Hopefully you can if you need to as well. So 2:40 p.m. is when I will come back. And thanks again for your patience for the long session today. Okay. Thanks again. Apologies. I get kind of my voice gets worn out going this long, but I also just think if I'm not done presenting it to you, I should just keep going and assume that if you got to get up and or you got to leave and kind of skip around in the video that you can do that. So thanks for your patience. If you're hanging around, I appreciate it. It's nice to have some people that sort of have in my back in chat, but um, so let's see what we can do to get finished. I am going to post these notes that I just made. Has that table, which I think is useful. So if anyone wants it, I'll post it on the lecture page. Okay, so let's finish the sort of lecture part and then look at a little bit of code while we're in there. So the organization. So I guess I'll just keep going down here and let me just push it up. So there's a weird thing in here that I'll tell you about when I get there, but the data organization simply means sort of in what quantities can we deal with information on an Intel processor, which is what I mean by x86. X86 is a term we use to refer to a whole family of Intel processors that go back into the early 80s that most of you, if you're a Windows user, you will have an x86 ancestor or descendant processor, a processor in that same family. A Mac, you may, if you have an Intel processor, have an x86, or if you have an M1, then you're off on a different architecture. But anyway, so in what quantities can we deal with information on the x86 processor? And sort of how do we what terminology do we use to refer to different quantities? So a bit is the least amount of binary data we can refer to, and we can refer to a single bit just by itself, or if we are looking at a larger value and referring to a specific position in it, we can say that bit right there, that's part of a sequence of other bits. We're still just talking about one bit. When we say a nibble, we mean a grouping of 4 bits. And that grouping is meaningful, as we just saw in our conversions. We don't just say any 4 bits. We mean 4 bits that are next to each other that are representing something specifically as a value. So a bit can be any bit, but a nibble is talking about 4 neighbor bits in a particular location in a sequence. And the way we'll write them in our class nibbles is 4 bits is a nibble underscore another nibble underscore another nibble when we're working in binary. So another way to say this is, I'll do it like this. 1 bit, of course, 4 bits. So a word, I didn't do a byte yet. I forgot a byte. That's 8 bits. Or 2 nibbles. A word is 16 bits, or 2 bytes, or 4 nibbles, if you do the math. And when I said there's something weird here about this, when we say word in x86, we mean a word in x86. There are processor families that when they say word, they mean a different amount of bits. I think in ARM, some ARM processors, a word is 32 bits and not 16. So when we say word, we mean a quantity of bits that's, and we need to be specific about the processor we're talking about. So for the Intel or x86 family of processors, a word means 16 bits. And it's important that we know that when we say a word, we mean a word for an Intel processor specifically, because other processors may use that term to mean a different amount of bits. Then we have a double word. which is 2 words and the rest of it, of course. So that would be 32 bits is a double word. We have a quad word, which is 4 words, and all of the other sort of increments that you could do the math on. Yes, so a single digit is 1 bit. It could be a 0 or a 1. And then I'm not going to do the math for the rest of those. And then some HLA data types, which we're not going to use just yet. A single letter is 1 bit. Well, you need to think it's binary, Druid. So we're talking about binary data, and they're not letters really. They're zeros or ones, and that's all they can be. So one position in any amount of binary data is 1 bit. And then when we have 4 bits together, we call that a nibble. When we have 8 bits together, we call that a byte. When we have 16 bits together, we call that a word, and so on. A char is char says, when we say char, like in C++, we mean an 8-bit ASCII quantity. So a char is an ASCII letter, and ASCII letters are represented in 8 bits, or a byte. And then we have bigger kinds of chars these days. So no, this is word just means in binary data. When we say word, we mean 16 bits on an x86 processor, not letters or characters or anything like that. 16 bits is a word. This is a particular application of this terminology. So think binary data. When we're talking about binary data, that's what these are referring to here. Binary data. Okay, so there are HLA data types for some of these, and I call these the raw data types. So bit, no. There's no type for bit in HLA. You can't create a variable of the bit type. Nibble, you cannot create a variable of the nibble type in HLA. So there is no way in HLA to declare a variable in your program that is a bit. And there's no way in HLA to declare a variable that is a nibble. But there is a way in HLA to declare a byte, and the data type is byte. When you see that data type, which will not be for a long time, but when you do see the byte data type, that often means I think of it just as raw data. Like, I don't know that there's any particular meaning to this information. It's not necessarily an integer. It's not necessarily a character. It's just binary data, raw data, as I call it. So a byte has a type. A word has a type. So that's the HLA data type for a word, which is a 16-bit amount of data. Yeah, so Evan, we'll talk about that when we talk about the integer types. But yes, the amount of bits determines, if you're talking about storing an integer there, how big the integer can be. That's true. I should put these arrows. I think that might help. So in HLA, if we want to declare a double word variable, that's called a D word. And in HLA, if we want to do a quad word amount of data, that's a Q word. We're not going to use these types very much, and certainly not anytime soon. But just so you know, HLA has data types for some, but not all of these amounts of bits. So there's no HLA data type for a single bit. There's no HLA data type for a nibble. But there are HLA data types when you get to the size of a byte and up. char is not raw data. So I'm going to do that here. Yeah, so Adeline asked if I'm going to post. I will post these notes. This document's gotten pretty long, but I'll post it at the bottom of the lecture page is where this will appear. Okay, so this was getting us into doing the code. So HLA data types for typed data as opposed to raw data. And what I mean by typed data is that when we declare variables using these data types, we know what we want them to mean. So someone asked about char. There is a char data type. And what we mean when we say char in our code is a single character. Now, what the computer does with that is something else entirely. But when we want to store a single character in our HLA code, we can declare variables using the char data type. It turns out that that requires 8 bits of storage to do that. We won't worry about that so much. But if we want a character type of data, then we will use char. And then we have a whole bunch of let me move these out. So hopefully everyone remembers what we mean by unsigned integers, which is they can't be negative. So in HLA, we have unsigned 8-bit integers, which is the range 0 to 255. And this is what someone was asking in chat, like does HLA have data types, and does the size of them sort of affect the amount of information that can be stored in them? And the answer is yes. So we have the uns8 data type, which is an unsigned 8-bit integer. And what that means is that we can use that data type to declare a variable that can only be used to represent the range of values from 0 to 255. We also have the unsigned 16-bit integer type, which can only be used to represent values from 0 to 65,535. So a bigger range of values. And then uns32, which is an unsigned 32-bit integer, which is 0 to a large number, which I can't remember off the top of my head, 4 billion or 4 trillion and something. It's a big number. It's a pretty large number. I'll show you where you can look these things up in a second as well. So this is kind of connecting back to just, okay, we talked about binary, we talked about bits, bytes, and nibbles and words and all that. But when we start coding this stuff, what is this going to look like? For us, for a very long time, this stuff in code is going to look like different kinds of integers of different sizes. What's important about the different sizes is that they limit or expand the range of values that you can store in them. We also have int8, which we're not going to use anytime super soon. That's a signed 8-bit integer, which goes from -128 to +127. So when we say a signed integer, we mean it can be negative, can have a sign on it. We have int16s, which is a signed 16-bit integer, which goes from, I want to say -32,768 all the way up to +32,767, I think. And then we have int32s. So these things on the left here, char, uns8, uns16, these are data types that we will use in our code. We're going to use a couple of them here in just a second. And And then byte, word, keyword, D word, and Q word are things that we could use for raw data, and we will later in the semester try them out. 0 to 255 is 8-bit unsigned. So there's a question about does it change the complexity of execution, the big O complexity, and the size of the values? Probably not very much. It probably doesn't change the performance of a calculation or an instruction being executed. All it really does is limit your problem space. So of the first two. Can you be more specific, Amber Wolf, about which first two you're talking about? Yeah, I'll do it in code. So I'm going to do an example of some of these data types in actual code so you can see them. And I don't remember the range on these, but I'll show you before I bow out where you can find the ranges of these. No, so Druid, yes, an 8-bit integer requires less memory than a 16-bit integer. But the question was about the performance of the processor on these different sizes of data, and that wouldn't really have any measurable effect, I don't think. Now, in terms of the memory used, yes, a 32-bit integer is going to chew up 32 bits of memory space, whereas an 8-bit integer will only chew up 8 bits of space. So these do affect the amount of memory and then storage being used, but they don't affect much the performance of instructions executing on them. Yeah, so if you wanted the value 5, you're going the smallest you can go for is an uns8 or an int8, depending on how big you think the value would get. So usually the size of these data types is more a matter of how big you think the value might get and not how small it's going to be. So if you know, for example, that you're never going to store a value that's not between 1 and 100, then there's no reason why you can't use an uns8. But if you think, well, most of the time I'm only going to have values between 1 and 100, but sometimes I might end up getting something that's closer to 1,000, then I can't use an uns8. I'm going to have to step up to the next size, which is an uns16. So yeah, yeah, that's a good way to say it, Druid. The upper limit of the values that you want to manage is going to determine the size of space that you're going to choose to use. So you'd like to use less, but you can't always use less because if you use less than you need, it doesn't work out for you. We'll play around with that in a program at some point so you can see what happens if you try to put 1,000 into 255. Yeah, so Evan asked, is uns30? So int32 is actually the C++ int because it's signed. Okay, so I'm gonna take all the blank lines off there because eventually I'm gonna. So this whole document, which I know is a mess, but it's gonna go up on the lecture page for this week, so you can all see it. And now we're gonna go switch over and do some coding where we can see the data types in action, at least a couple of them. So I'm gonna switch views real quick and go show you where I'm getting what I'm getting, and then I'll come back. So first thing is, let me switch views. Get my browser up. Yeah, I hope no more than like 5 or 10 minutes because I got another class and I need to rest my voice. But I also want to get you where some people are going to want to see some of the labs. So I feel like I've got no choice but to just knock it out. What am I doing? Oh, switching views. So I will show you real quick that you can Google search integer computer science, which will get you the Wikipedia page about integer computer science. And if you scroll down here, you will see that it describes to you the sizes and the range of values that they represent, what they look like in different programming language and stuff like that. So anyway, integer computer science on Wikipedia is a good reference for getting a handle on what the size of an integer and the values it can store represent. Okay, now where I'm going to go a little bit quicker. So I'm going to the lab page. I'm going to get the starter code, and I'm going to go back over and plug it in. Oh, there's not much here. So what does it want me to do? I'll have to, you're not going to see me switch back and forth a whole lot. Declare some variables, a char and two uns8s, output a greeting, a forever loop, a repeat until loop. So I'm not going to have time to do, I'm just going to give you a couple of quick examples so we can end the stream of what the high level stuff looks like. But I have linked you to readings that show you how to set up if statements in HLA and how to do loops in HLA. But I'll get enough to give you a bit of an example, and I'm going to go kind of fast to get us through. No, the questions are good, so I'd rather go long and have questions than sort of blast through it when people do have questions. So I think the questions are super valuable, and I think it's worth the time to take to answer them and try to answer them carefully before I sort of motor along. So I appreciate them, and I know it makes the experience longer for people, but I think it's worth it. So, and you guys, of course, can always bow out when you want to, and then kind of chop up the video and view it at your leisure. Okay, so I'm gonna, how do I want to do this? Yeah, I'm gonna close this for now, and I'm gonna go through the process quickly of setting up my lab too. So I'm gonna create a new folder in here. I am in the CSCI 10 folder. I've created a lab 2 folder inside of it. And then I'm going to go to the lab 2 folder. I am going to use the file menu once I'm in the lab 2 folder to open a terminal here. So the terminal's in lab 2. The file viewer is in lab 2. I'm going to open the code editor here. I am going to create a new file. I'm going to call it lab2.hla. And it's going to bring me to this file dialog saying, okay, I got to create this file. I make sure it's in the lab2 folder, which it is. It's called lab2.hla. That's all good. Right, here we are. And then I have copied the starter code. I don't want to update now. Just go away. 30 August 2022. All right, so here we are in lab 2, and I'm going to do some of the lab requirements, which is basically read a couple of integers in, compare them, and then output if one's bigger than the other one, or the other's bigger, or they're the same value. So we need to Control S to save. We're told to create variables. So in HLA, when you're going to create variables, we're going to come up here between the opening of the program and where the block begins, the main part. I do it under the include. So right here, I'm going to set up a section, which you can do in HLA, called static. And this is where my variables are going to go. So I am going to create a, I'll call it a X, which will be an uns8. I'm going to create a Y, which will be an uns8, which is what I'm told to do in the assignment. In HLA, variables are given 0 values if they're uninitialized. So HLA will make X be 0. C++ would not do this. HLA will also make Y be 0. And then I'm also going to create a, I'll call it choice, which will be a char. So there's my 3 variables I'm supposed to declare. Notice in HLA, the name comes first, followed by a colon, followed by the type. Yeah, so there's my 3 variables. I'm told to print a greeting. Put a couple of new lines after that one. So again, I'm kind of going quick here because I want to get the stream done, because some of you guys have been sitting here for a very long time. Plus, I need to rest my voice for another one that's going to be similarly long here in just a bit. Okay, so all I've done is done what the lab told me to do, which is declare these variables, 2 uns 8s, which are x is an unsigned 8-bit integer, means it can be used to store values between 0 and 255. Between 0 and 255, and this is the ASCII character set, which is more or less what you can see on your keyboard. And that's the variables for this program, all declared in this static section. I'll put this in the code samples as well, what I get through. All right, so now we're going to do a couple of loops. And this is like a do-while loop. So it's a do-while loop, but in HLA we call it a repeat until loop. And remember, in HLA they don't use curly braces, so the way that they mark the beginning and ends of things is different. But writing the logic is very similar. So I'm about to put a loop in here where I'm going to ask the user for a number, and I'm going to stick them here until I get what I want. Which is a value for x between 1 and 50. Now we're going to do a couple of things that are going to be a little bit different, and we will explain the details next week. So enter a number between 1 and 50. Let me stretch this out a little bit. Now I'm going to do a couple of things that are going to look a little bit goofy at first. If you do not put this flush line in before you do a keyboard input, you can have problems. So this is here to avoid any weirdnesses with the keyboard input. So just before you ever do any input statements, do a flush statement, and you'll see me do it in my example here, and then you won't have problems. And I'll explain the details next week. For now, I just want to get you, you can read about all this, of course, but I want to get you through something that you can work with to finish the lab. All right, now the weird looking stuff. So I am using an HLA routine to read specifically an unsigned 8-bit integer from the keyboard. If the person type something that's not an unsigned 8-bit integer at the keyboard, the program will crash. But I want us to get in the habit, and then I will show you how to make it even better later. But I do want you to get in the habit of thinking about the data types we're using. So I am reading an unsigned 8-bit integer from the keyboard, and I'm just warning you up front, if you try to type something in that's not an unsigned 8-bit integer, the program will throw an exception and shut down, which was what we want to happen. But if you don't remember and you're goofing around, it can be irritating. Okay, so now a very assembly language looking thing. I'll tell you what it is, and then I'll tell you what it is in more detail next week. So this little pair of lines of code works together. So what happens is this get U8 will read an unsigned 8-bit integer input from the keyboard, and then it will actually store the value on the processor. Somebody mentioned registers earlier. This routine actually stores a value in a processor register, which is a data bank built into the processor itself, which is a very assembly language thing to do. So don't get hung up on it too much. Just kind of note, we're actually right now in these 2 lines of code interacting directly with data on the processor. So we use a library routine that's going to accept keyboard input and store it on the processor. And this next routine is actually an assembly language instruction that says move, but is actually a copy. Why, I don't know, but the instruction is move, but what it actually does is it copies a value from a location on the processor, which we refer to as AL. It's a hard coded location on the processor. So we're copying a value from the processor into our variable. Kind of crazy. So that already is an assembly language instruction that is copying values from processor data registers or memory locations into our variables. And there we have it. It's going to keep bothering them for that until they type in the number. So you're going to have to repeat that entire process for the Y. You're going to have to do a repeat until loop, enter a number between 1 and 50, standard out in.flush input, standard in.get U8, the move instruction, which will copy the data from the keyboard that's been stored on the processor itself, copy that into the Y variable. Then we do the process of comparing the 2 values. And this is also going to require something weird. So this is a huge moment. If you don't do this, you are going to fight with this lab. You have to do this. You have to copy. So notice I'm going the other direction now. Now I'm copying my X variable value back onto the processor. If you don't do this, you're going to get errors. So you have to do this step for this to work. And this is an assembly language limitation, which we'll talk about next week. But you need this line or what follows doesn't work. And then we're going to compare the X value, which is now in the processor, to see if it is greater than the Y value. No. So Adel asks, are we leaving a bunch of X's around? No, there's only one X. And there's only one AL on the processor. So that's 2 locations. And we're just copying data back and forth from one to the other at different timings in the program. So notice here, so this line of code right here is copy the value of X to processor register AL. We'll talk about processor registers next week, but it's a memory location on the processor. You do not. So Magenta asked, do we have to move Y in the other direction? And the answer is no, we don't. Just the X. And I'll talk about why we're having to do this. And I'll show you the error next week since we went a little bit long today. And then some of the weirdnesses of HLA. So just make note of these things and you'll have the reading linked, which you might keep open as a reference because you'll need to get used to how to write an if statement in HLA. But it's critical that we do this step or you're going to get errors. So make sure that you get line 27. I will post this sample in the lecture notes. And then notice the way else ifs are done in HLA. It's all mushed together, else if. Yeah, so that's you actually, Magenta, you landed on exactly the thing. Um, HLA will not allow us to compare two variables to each other. So we actually have to take one of the variables and put it on the processor so that we can compare the two values, which is actually a thing that Intel assembly won't allow. So Intel assembly will not allow us to compare two variables directly. We can compare a variable to a value that's been copied over to the processor, is the way we have to do that. And that's actually a limitation of Intel assembly, the processor itself. And HLA imposes that same limitation on us. So if you were to try to compare X and Y as the variables, you'll get errors saying you can't compare two variables. No, so Druid, you can copy two values to two separate registers, which we'll do eventually, and compare them that way. This is just to keep it from being overly complex. So we can't compare two variables to each other. We can compare a variable to a register or a register to a register in Intel assembly. It's actually, I assume it's actually faster for the processor to execute the instruction with not having to fetch two variables from memory, which requires time. Even though we have to do a move instruction to make a copy, I think that's actually been optimized on the processor. So this separate move is actually faster than if they had tried to build circuitry to allow us to compare two variables, is what I think is going on. Okay, so I hope that's enough for everyone to work with, and I'll post that as the code sample. You have readings to help you. The thing to pay attention to is just the little bits. Oh, you're supposed to do a. Sorry, let's finish with that. You are supposed to do a forever loop. I love this feature of the HLA language. So you're supposed to wrap that whole sequence inside a forever loop so someone can just keep comparing numbers and comparing numbers and comparing numbers forever. What's cool about it is that it is, by design, an infinite loop. So how do you get out of this infinite loop if it's designed to work this way? So here's how we'll do it. We will ask the user if they want to go again. Make sure we do a flush before we try to do a read. We will get a character this time. And then we will copy the character value from that same location in the processor, as it turns out, into our character variable called choice. And then we will say break if choice is a little no or choice is a big no. They didn't want to go again. So this break if construct will break the forever loop, which is pretty cool. Choice is defined. So good question, and you probably lost track, but I did define choice as a variable at the top, which you'll find when you see the sample when I post it. So yeah, choice is declared as a character. Okay, so there's a lot going on there. I hope that next week I have time to to break this down. So don't forget, you have Piazza that you can go out to and share help with each other about how to complete this lab. I hope that most of what you need is here to complete it. If they say no, we quit, right? Yeah. So anyway, here's a little bit more HLA syntax. I have given you the forever loop that's required and the means of getting out of it. I have given you one of the inputs, the X input, and then I've given you the setup for the comparison part, and then one example of an output to get the information out on the screen. So I hope that's everything that you might need to complete the lab. And we went for a very long time today. So thanks for your patience. Thanks for sticking around. If you could stick around, all of the notes from earlier will go up. This code sample will go up, and then the video it'll be later this afternoon or evening, because I got to start up another stream here not too long from now. So that's a lot. I don't think every week we're not going to go anywhere close to this, but I will go as long as is needed to address your questions. So I love having the questions. It's enjoyable for me. And I hope it's not grinding anyone out there down too much to go this long. Anyway, so I expect, though, that some weeks will go faster than others. This one is about as long as I've ever gone in a lecture for this class. So that's good. We had a lot of questions, and hopefully the answers were good and usable. So yeah, that's it. Have a great week. If you're watching the video later, sorry that it's such a long video. Hopefully you could stop and take breaks and come back to it later. Don't forget Piazza, not just for discussion, but for asking and sharing questions. I have had students put markers in Twitch on the video so that other people can know where things are happening, and you're welcome to do that, of course. So anyway, that's it. Need to rest my voice. I'm sure you want to get up and get away from the computer for a while. So thanks for being here if you could. Thanks for watching the lecture all the way to the end. If you're doing that later in the week, and otherwise I will see you on Tuesday next week. Take care.